Our last speaker of this session is Raquel Alonso-Perez, and she is the curator of Mineralogical and Geological Museum at Harvard University here in the United States. And her special interests are the non-destructive and analytical techniques in use to study gem deposits. And so I'll turn the podium over.
Thank you.
Thank you very much.
So thanks GIA for this fabulous symposium, and today I'm not gonna be a conductor. I'm gonna be playing to my main strength, which is geochemistry. And I have been known for sending people to sleep, especially before lunch. So I'm gonna start my talk with my summary. This is the first combined study using solution, ICP-MS and Raman spectroscopy on emeralds. The trace elements reveal provenance, and rare earth elements are petrogenetic indicators. Also very important, couple OH stretching vibration with major elements give us very crystallographic insights. Now, during the course of my talk, I'm gonna focus on these three main questions. I'm gonna touch about what are the relationships between elemental constituents and the crystal structure. I will also try to answer and touch a lot about the topic that we have seen this morning, which is, can we use trace elements for provenance? And very important as a geologist, in what environments these emeralds form. Now, currently, there are around 20 gem quality emeralds deposits in the world. And although not described in here, but mentioned this morning, we have the ones in Canada, in the Yukon, but also in North Carolina, the Green Beryl, and in Norway. And the ones we have chosen for this study are probably the most representative deposits, and those are the ones from Colombia, Brazil, Madagascar, Zimbabwe, no, actually no, we didn't use Zimbabwe, we used Zambia, excuse me, Nigeria, Egypt, Austria, and Australia. Now, on a very broad, raw classification system, all these emeralds have been classified in two type deposits. One are the black schist type deposits, the black shale, excuse me, and the other one, the schist type deposits. Now, Colombia is probably the typical and the most common black shale deposits. The emeralds are formed in a sedimentary sequence by hydrothermal fluids. These fluids carry also a sedimentary fingerprint, which comes from the evaporites and also some shales within the deposits. On the other hand, the schist-type deposits are shown here by Egypt and Madagascar. They are formed in a very different environment. The emeralds are found in what is called the black wall. And this is a actinolite phlogopite-rich metasomatic form due to metasomatism between a mafic and an ultramafic rock. Now, most of the deposits that we saw from Madagascar, Zambia, up to Tanzania and Egypt, you have to think that they are formed around the same time, 550 million years ago, during the formation of Gondwana and the collision of the Mozambique belt. And what we see is that on these rocks, they have a very high schistosity on them. So that's an evidence, a geological evidence that these rocks were formed under regional metamorphism and probably very important tectonic events. Now, if we look more into detail about all these classification systems that have been studied by many authors, as Lee Grosso pointed out this morning, they are basically two types again. So we have the Colombian black shale deposit, which was originally described by Terry Ottawa here on the audience in 1994, and that one is very clear and evident. And the other schist-type deposits can be classified as a pegmatites without schist, pegmatite with glycine and schist, schist without pegmatites, and schist without pegmatites with different kind of degree of interaction of calcite and talc. Also, Lee Groth did a study on emeralds where he looked at the oxygen released by the emeralds versus the oxygen released by the emeralds at 100 degrees. And more recently, there is also a study by Sims that looked at some of the major and minor elements in another suite of emeralds. And they come basically to the same point, that there are two classification descriptive systems. So overall, there isn't any genetical model. We really don't understand how this emerald form, neither the environment under which this emerald form. And trace elements, because they are in very low concentrations in the emeralds, they are key indicators of the provenance of where they come from. So we decided to do an inductively coupled plasma mass spectrometry study. And in this case, this morning you have heard a lot about laser ICP-MS. What we did is solution ICP-MS. So unfortunately, we have to sacrifice 47 pieces of emeralds from all these localities. But the idea is that you get really high concentrations of those trace elements. So you get much better accuracy of the signal that they are giving you. Now, we are also in collaboration with GIA and a few other co-authors. We are working on developing a system so we can use solution versus ICP-MS, and these are the recent results. So please take a look at the poster in 105, because there is a lot going on how we can put this method together, so we don't need to sacrifice more emeralds. Now, we also did a Raman spectroscopy study, and the idea is that we get a lot of information when we look at the spectra of emeralds. This is a typical Raman of all the emeralds from the study. Now, going straight into the data and looking at the trace elements. This is a very busy plot with a lot of information, and I'm going to break it down into a few parts and walk you through. But kind of first observation is that we order the elements based on relatively compatibility. So the ones above the line number 1, it means they are more compatible in the emerald. The emerald likes those elements. But if you go down here, and those are the rare earth elements, they are in very low quantities. Another thing to note in here is that we normalize the emeralds to continental crust. You might have seen in many trace elements they use chondrites. But that's widely used, but it's probably not correct, because the most likely source for an emerald is a continental crust. So if we kind of parcel out this plot and we take a look at the relatively compatible trace elements in emerald, we see that they have high cesium, high lithium, high rubidium, and high lead. But especially high cesium, lithium, and rubidium for every locality except Colombia. So it's very easy to distinguish Colombia, and that's clear because we saw they form under very different conditions. Now, someone asked before about the chromium-vanadium ratio from Egypt, and it's interesting because the chromium-vanadium ratio for Colombia, as you can see, is very small, where for any other localities, the slope is very high. So there is a much more high chromium-vanadium ratio for other localities. Interesting enough is that Colombia emeralds, they tend to have a high lead. And as you know, the way they mine in Colombia is they analyze the soil. So if the soil has less lead, they know there are emeralds in there, because the emeralds, they tend to suck up the lead. So we can tell a lot about trace elements. And something that we didn't talk about, but in terms of geochronology and try to date the emeralds, previously has been used rubidium strontium ratios. And for Colombia, those ratios are very small, where for the other localities, the ratio is much higher. So that's a method that we should be careful of. And if we take a look at the rare earth elements, which can be divided into the light, lanthanum, cerium, precision, and neodymium, and the heavy rare earth elements, we see two very interesting things, actually three. One would be the European anomaly. So as you can tell, all of them display European anomaly, so it's negative, except for Colombia. Colombia also has a very generous, relatively flat pattern, which that makes sense. So in terms of absolute concentration, you see this is number one, so this is our continental crust. Colombia is very flat, but much lower. So it's telling you that the source of these emeralds is very similar to continental crust, so sediments, black shales. Very nice, described the model back in the 1940s. Now, what is very interesting for the other localities is that if you look at the pattern, it goes very flat, and then there is this upturn for most of them, for the heavy earth elements, the erbium ratio over ytterbium. And I'm going to tell you later a bit more what that ratio might mean, or what we think it could mean. Now, moving into Raman spectroscopy, we are not going to talk about burial structure, which is much simpler than the tourmaline structure, but they also share a nice, interesting feature, is that along the emerald, there are some channels formed, and those channels is where the water and the alkalis go. And those channels has been described as the type 2 channel, where the emeralds are alkali-free, and the type 1 channel, alkali-free, and the type 2 channel, where you have only alkalis, and water and CO2 and methane goes. So this is a typical Raman spectra, from 250 to 3,900 centimeter Raman shift, and the intensity is arbitrary units, although it gives us a lot of information. Now, one thing I forgot to mention is that there is a crystal orientation dependence with Raman spectroscopy. So we did two sets of measurements, one parallel to the z-axis and another one perpendicular to the z-axis. So for all the next data I'm going to show you, we just use all parallel to the z-axis, so we get the maximum intensity. Now, I'm not going to focus on the first part, which is considered the fingerprint, but I'm going to focus on the OH, which are going to give information about the alkalis and the CO2 in the emeralds. So before you couldn't see much difference, but now if you zoom in and you take a look at the different localities, what is clear is that Zambia, Madagascar, and Egypt, they have a very strong type 2 water, and they are actually the ones that have a lot of alkalis and sodium on them. On the other hand, Colombia has a very small type 2 water peak and a very high, strong type 1 water, which is the alkali-free channel. So going back to my questions, I postulated at the beginnings, what are the relationships between elemental constituents and crystal structure? Well, if we take the maximum ratio between type 2 and type 2 water versus sodium, we see there is a nice, clear correlation, a strong positive correlation between those two. So it's clear that they are sodium, so Colombian, are much less alkali-rich than the one from Zambia and Madagascar. Interesting enough is that iron is also showing that positive correlation, which might mean that the iron goes opposite to the cobalt spinel we saw from Aaron this morning. Iron 2 plus might go in the channel, and that's what we're seeing here, because if it will be iron 3, that will go in the oxidal side. So it's just, we get a lot of information from Raman spectroscopy. Carry on with my next question, can we use trace element for provenance? Well, I think we do. There is a lot of promise to do that. And going back to these 8 elements that they are relatively compatible in emeralds, we see how Colombia, Egypt, Madagascar, and Zambia, they are quite distinct. If we look at the ratios of cesium versus chromium normalized to continental crust, and rubidium versus chromium, and vanadium versus chromium, you see how they really, all those different localities, they are quite distinct. And into my third question, in what environments do these emeralds form? And this is the two things I point out before from the rare earth elements. The European anomaly that we see in here, except for Colombia, and this upturn on erbium and ytterbium towards the end of the heavy earth elements. Well, if we look at minerals that can fractionate those elements, those are plagioclase and garnet. So in this lower plot, what we see again is the rare earth elements versus KD. This is the partition coefficient for those minerals. So you can tell that plagioclase, it tends to fractionate europium, where garnet, it tends to have an increasing pattern of fractionating those elements. So basically, the signature of these emeralds, at least for all the ones that we study, except Colombia, they are showing an environment where plagioclase was removed, it stayed as a restitic, and then the fluids that we're going through, they broke down the garnet, so they have a garnet signature on them. And one of the most plausible environments to do that is in subduction zones environment. So this is a possible tentative petrogenetic model, so moving away from descriptive classification. And what we can say is that Colombia was formed by hydrothermal brine transport from evaporites and thermochemical reduction, releasing trapped chromium, vanadium, and beryllium from sediments, and that was beautifully done, and kind of we can test that by the trace element. Now, on the other hand, Madagascar, Zambia, Egypt, they seem to be coming from a sediment-rich subduction environment and generation of beryllium-rich fluids interacting with mafic, ultramafic complex during regional metamorphism. So coming back to my first slide, this is the first combined study using solution, ICP-MS, and Raman spectroscopy in emeralds. Trace elements reveal provenance, and rare earth elements are really good petrogenetic indicators. Couple OH stretching vibrations with major elements can give a good insight of the crystallographic of emeralds. Thank you.
Thank you very much, Raquel. Do we have any questions?
Emmanuel. Okay.
Yes. No questions?
Well, there's one
Okay, one
Emmanuel.
question.
Okay, Raquel, you mentioned the use of Raman spectroscopy and you illustrated it with water.
Yeah.
What else can you do with Raman spectroscopy besides water?
We have a master student looking at all the spectra. Like you mentioned about the chromiates, how the chromites from the Jedi before, they were quite different. In this case, all the emeralds are almost identical, but there is all these nuances of shoulder and peak. So you can tell a lot about the structure of the beryl. Do we have all the alumina on the octahedral side, or do we have any replacing on the tetrahedra? Is the beryllium in the same site as the silicate, or has its own site? So there is a lot of information we can get with Raman.
Okay, thanks.
Welcome. Thank you.
Any other questions? Yes, Clemens?
Okay, I'm coming. I know you're at the front. Just out of curiosity, when it comes to the Petrogenetic models you did you also look at emeralds from Afghanistan and Malaya?
No.
Okay.
So this is the thing, we are missing some localities, and I kind of raised up also Ligro. Like, I know many emeralds have been studied by labs, so if we will use those emeralds that have been well studied for our study, then we could really move forward.
We can help you.
Yeah, thank
Pleasure.
you. I'd love to. Thanks.
Any other questions?
There's one more.
Yes.
Great talk. Thank you very much. Muzo, Colombia is the global type locality for the rare earth mineral parasite. And the greater the parasite, the greater the emerald grade. What do you make of that?
remind me again, what's the mineralogy of that mineral?
Parasite is rare earth fluorocarbonate.
Fluorocarbonate. Okay, that won't make sense because what you see in there is on these black shades and evaporite, so it's typical of carbonate sequence.
The higher the rare earth concentration, the higher the emerald grade.
I think it fits with the paragenesis, but I don't know.
Another question?
Thank you.
Thank you very much, Raquel.